Hello everyone. Today we will be talking about system level experimentation. I will be mainly discussing pricing in FoodTech, but basically we will be looking at some general ideas that can be applied in many different areas of FoodTech or in many different other business applications as well. So let's start. First of all, let's discuss what is the task that we are trying to solve and what is the actually goal that is tried to achieved by pricing in food tech, and what does pricing mean at all. So here we are talking about delivery pricing. That's the amount that users pay for their orders to be delivered from restaurant by on some platform. You probably know some platform, you probably used some of them. And what are the goals that are usually aimed at by different pricing methodologies, by different optimization algorithms. There are two types of goals. They can be broadly split into two different groups, like short-term and long-term. And short-term goals usually involve total revenue optimization, which is more or less local problem to solve, while long-term goals usually involve such things as users lifetime value optimization, and these are a bit complex in terms of modeling and in terms of the way how this thing that is called LTV or lifetime value can be estimated. Thus, it is a bit more complex to optimize as well, and it's a bit different area. Usually, it involves more like strategic decisions or business development teams. So today we will be talking about mainly the problem of short-term revenue optimization and what are the trade-offs that we have. So basically they are, again, if we consider only short-term revenue, they are quite trivial. So if you increase delivery fee too much, so if you charge too much from users for delivery, then you have revenue growth per order, but the number of orders declines because yeah, it's obvious. So if your delivery fee decreases, you have the opposite effect, which means that basically if you imagine that your delivery fee is too low or too high, then you have non-optimal settings that lead to negative impact on your revenues, meaning that somewhere in between there is sweet spot where your revenue is optimal, meaning that it's the maximum that it can be for the given environment. This is the trade-off that we will be mainly discussing, and one of the core concepts that usually are looked at in that context is elasticity, demand elasticity, which describes how much your number of orders or conversion from a user opening a new session into a user making an order changes if you change your delivery fee. So that relationship is, as I already mentioned, obviously monotonically decreasing, which means that the higher delivery fee you have, the lower is the number of orders that are going to be made on your platform. But locally, if you consider only small changes, it can be usually approximated quite well with some linear function. And yeah, obviously for large changes in delivery fee, that probably doesn't work very well, and you will have probably some non-linear, some convex dependency. But for very small changes, you can basically assume that what you really need is just a single number that describes the first derivative of that dependency of your demand on the average delivery fee. So how can that be estimated? There are two main ways that we will be discussing now. One is A/B testing, the other is switchback testing, and there are some other ways, some parametric ways to estimate that dependency using some assumptions about the model that describes your demand. But today we will be just discussing experiments way of doing this. So what are the tests that I just mentioned, and what is the main difference? What is A/B versus switchback? A/B is a very simple setup based on simple user randomization. You basically split all users that you have into two groups. For one group you say that you don't change anything. For other group you increase your average delivery fee in some way. Actually, that's very important question, how you change your delivery fee, because that also obviously affects the orders and user behavior in general. But for now, let's assume that you have some change of delivery fee in average, and for simplicity you just increase all orders delivery price by the same amount, which is equal to that average. What is the main disadvantage of A/B testing in that setup is that users are in reality not independent. So A/B tests, pricing A/B tests can work well if users are independent from each other, meaning that decisions of one user do not affect the system for the other users. But this is not the case, because the FoodTech is actually a quite complex three-sided marketplace, which has also restaurants, which also has couriers, and quite often the main bottleneck is the supply side, not the demand for the growth of business. And if you increase for some group of users price, then obviously that leads to less orders from that group, meaning that you have additional courier capacity, excess courier capacity that is freed because of that change for half of your users, which means that it's actually easier to find a courier for other users, and that means that you actually unintentionally improve experience for them. You unintentionally, actually depends on your pricing algorithm, but maybe you even additionally decrease the price for them based on the fact that you take into account, for example, how far the nearest courier is from the restaurant from which a user is trying to order, which is not what we want. We want a fair experiment which doesn't take into account any additional effects, that really estimates the impact only of the price change and not anything else that comes together. And for that case, on the right hand side of that slide, in FoodTech, switchback experiments are quite common. So what is a switchback experiment? Instead of splitting all users into two groups, you basically split your timeline of the experiment. You use two pricing algorithms alternately, and within each period of time, you price all orders using the same algorithms. So either you increase price for all orders or you don't do anything. So in this example, I basically tried to highlight how that can look like. You can split, let's say that your experiment lasts for 2 days and you split your 48 hours of the experiment into 12 blocks, each one 4 hours length. And within each of them, you basically have either one or another setting. What is the main question here is obviously how to choose a window size appropriately, and here is the trade-off between either too noisy results or the opposite, some effects that are obtained only because of some like local seasonality within that overall experiment time span. So if that window size is too large, then you basically may end up with unreliable results that are not related to your change. If it is too small, then basically you just will have too unstable and results that are not related again to your change because your system didn't really react. So how to solve actually the first problem? Sometimes what is done is to avoid that like local seasonality within a day, which is like for example due to lunchtime or something else, you can flip the mode. For example, during night when you have an overall very low number of orders, you can basically in that way switch the order in which algorithms are applied between one day and another. And it is usually recommended to conduct switchback experiments for at least 2 weeks, so that each day of week can happen under both modes, with like flipping somewhere in between. How to evaluate results of a test, of an A/B test? That is a like simple statistical problem that has been solved a lot of times with many different classical statistical tests. So you basically assume that under the null hypothesis that there is no difference, then you build some statistic, then you say, okay, if my null hypothesis is true, then my statistic should have some given distribution, and if the sample value that is computed based on my actual experiment results is too large, then probably my null hypothesis is not true, meaning that I have some non-trivial impact from the change that I did. And some examples are on the site. So some examples are two-sample t-test, a little improvement over it that allows to avoid assumption about variance equality between two different groups is Welch's test. Also there is Mann-Whitney test, permutation test, but they all are doing approximately the same thing that I just described. And each one of them can be applied to many different characteristics of orders. For example, you can test how the average order size changes, how the revenues or profits per order change. You can test how the conversion of users into order changes, the probability of a session to end up with an order, and many other things. And overall, that will allow you to have an understanding of how the total revenue will change if you roll out your change, you roll out your price increase or decrease, or any maybe less trivial change of the pricing algorithm for the whole user base. So with switchback tests, it's a bit more complex, and results evaluation is a problem that is known as the change point problem in time series analysis. So basically, you need to identify the times when the distribution of the orders or sessions or any other objects that you link to the final order that is being made change in time, and to make a step back. So in general, switchback testing allows you to pick up more than just the change in averages compared to A/B tests. It allows you to discover changes in variance and changes in frequency of the stochastic process as well, which is a better description of the behavior that you may find also important. And in that concrete case, I have here a small comment that even though we know when the change is assumed to happen, because we know what are the windows that we use in the switchback experiment, First of all, we don't know whether that experiment is affecting the metrics that we are interested in. We don't know the size of the jump, if it will be statistically significant, and we will discuss how to estimate the threshold, which to consider to be like the lower bound of a statistically significant change. And yeah, that's basically a common framework of the change point problem. So how to solve it? Switchback tests usually, and the common approach to solving them, the change point problem in switchback tests, is based basically on maintaining some window of observations to compute some average, and this average can be either computed as a simple moving average, meaning that it's like just the simple regular arithmetic average of the observations within the sliding window, or you can also incorporate some model like exponentially weighted moving average or Garch model to also compute that mean value. And yeah, that's the approach. So basically the main question, as I already mentioned, is how to choose the threshold for the decision about a change point being discovered to be made. And that threshold can be computed with the following algorithm. So you just choose some recent period of stable regime, meaning that this is a period when you did not make any interventions, you did not change pricing. You split it into windows. It is recommended to split it into windows of the same size. You compute average for each window. Also, it is recommended to compute it in the same way as you are going to compute it within the sliding window that you are going to maintain. And then you just compute pairwise absolute differences between the windows of that stable regime period to basically have an estimation of empirical distribution of those differences if there are no interventions. Then the approach is to choose a quantile of that empirical distribution as a threshold. Usually it's like either 0.95 quantile, so that it's relatively high to avoid some false alerts. And after you chose that threshold, basically the change points that you will discover based on your time series of the incoming orders, for example, can be validated against the experiment periods, meaning that you can just check whether the regime changes that you find match the moments when the experiment was flipping the pricing algorithm that is used. And the impact estimation, if you use that algorithm, is also quite simple, and it's just the difference that turned out to exceed the threshold. And at the same time, what is important is that you can maintain like a monitoring system over multiple different characteristics of orders, which can also track absence of any negative impacts produced by your intervention, produced by your like experiment. That's it. That's basically everything I wanted to tell. And just to sum it up, AB experiments do not work well in complex systems because of interdependencies. A better way to conduct them is switchback testing. And one of the common views on results estimation after you conducted a test is a view from the change point statistical time series problem perspective, which basically allows you to estimate the impact, to validate your experiment, to estimate any unexpected negative impacts as well. And that's it. Thanks everyone.